Okay, we're on page 6. We're going to have a look at the 2020 Extension 1 NESA sample HSC. They produced question 13b. It was a big 4 marker, and I think it's an interesting auxiliary angle question. So, a device playing a signal that's given by this produces distortion whenever the absolute value of x is greater or equal to 1.5. And remember, if the absolute value of x is greater than or equal to 1.5, that means that the distance from the origin is greater than or equal to 1.5. So that means that we could be here or we could be here. In other words, x greater than or equal to 1.5 or x less than or equal to negative 1.5. Okay, 2 sections, 2 inequality. So that's what that means. Then the question asks, for what fraction of the time will the device produce distortion if the signal is played continuously? So what fraction of the time do we have distortion? Okay, so the first thing to note is that nowhere in this question does it say anything about using auxiliary angle method. Okay, you should recognize by the fact that there's a sine and a cos that have been added. They have different amplitudes, but they have the same period. So sine and cos added with same period, it suggests that if I want to do this question, I'm going to want to use auxiliary angle method. Okay, so the first thing I'm thinking about is using auxiliary angle method. And look, that might not be apparent to you, but with enough practice, if you see sine and cos added together, 2 terms, sine and cos with the same period, you should think auxiliary angle method. So we're going to write that as R. Now, because it's positive sine, I'm going to use sine. I'm going to choose the one that will make the auxiliary angle acute. Keep the same period, so write T. And then, because there's a plus in the middle, I'll put a plus alpha here because we're using sine. Okay, let's expand. So sine of the first, cos of the second, and then plus, I'm going to expand that R, cos of the first, sine of the second. Let's equate. The sine t is going to be, coefficient of sine t is root 2 is equal to, on the other side it's r cos alpha. Let's equate coefficient of cos t, we'll get 1 is equal to, that'll be r sine alpha. Okay, what's nice, remembering that r is positive, is that cos is positive and sine is positive, so therefore for alpha we have to be in the first quadrant for our auxiliary angle. Okay, now I'm going to call the equation with sine 1, call the equation with cos 2. To work out r, you always do square root the root 2 squared plus and coefficient of cos there, which is 1 squared. Now be careful here, that's squaring, that's going to be 2, squaring, that's going to be 1, so it's going to be root 3. So r is root 3. And if you do 1 divide 2, we'll get that sine divide cos is 10, the r's cancel, we'll get 1 on root 2. Now that's not actually an exact value. Okay, we can just write this alpha as inverse sine 1 on root 2. Actually, I think what you'll find for this question is the alpha is not going to be so important, so I'm just going to, rather than writing inverse tan 1 on root 2, and by the way, you're allowed to move the tan to there because we know we're in first quadrant. So that's within the restriction of inverse tan. Okay, when it's quadrant 1, you can just move that tan over. All right, so therefore, what we've got that x equals to r, which is root 3 sine t plus, I'm just going to write alpha. I'm just going to leave it there, where alpha is inverse tan of 1 on root 2. Now, so what we want to know, let's go back to what the question is asking. What fraction of the time will we produce distortion? Remember, distortion occurs whenever this happens or this happens. when the signal is played continuously. Now this is a sine graph, okay, so this is going to look something like this continuously. Convince yourself that if you we don't need to focus on there's no domain here. What we can do is if this thing is played continuously, it just repeats one period over and over again. So you could answer this question instead of what fraction of the time will produce distortion if it's played continuously. We could say what fraction of the time if the signal is played for one period. If this says continuously, it's going to be the same answer for one period. Okay, because after that it just gets repeated and repeated. The fraction will stay the same. So we'll just look at one. So we're only going to look at one period of the graph. So what fraction of the time is this occurring in one period of the graph? And the other thing to note is that it actually, one nice little trick here is to realize that because we're focusing on one period, we're focusing on one section. How far this is shifted left or right doesn't matter whatsoever. So the phase shift is not important. So for this question, the phase shift is not important. Okay, because we're still just focusing on one period. It doesn't matter how far shifted left or right we are. In terms of all we care about is for what fraction of the time are we greater than 1.5 or less than or equal to negative 1.5. So what I decided to do is I decided to let t plus alpha equal to theta, and that just ignores the phase shift altogether, so that we get that x is equal to root 3 sine theta. Okay, now we want this. Okay, we want to know what fraction that over the total period. So really what we're doing is I'll look at the boundary, and then I'll also look at the graph. So the boundary will have this equaling to 1.5, which means that we've got absolute value of root 3 sine theta equaling to 1.5. I might change that 1.5 to a fraction, 3 on 2. Okay, removing the absolute value, I'll put plus minus. Okay, I might divide by root 3. I'll rationalize. Now we've got an equation we can solve for theta. So you'll have plus minus 3 root 3 on 6, which is root 3 on 2. Well, that's nice. That's actually an exact value. So we've got sine theta is equal to this. Okay. Now, because it's plus minus, all stations are central, all 4 quadrants will have a potential answer. And we're only focusing on one period, so we're only going to go around the circle once. So related acute angle, root 3 on 2, root 3 on 2. That's pi on 3, isn't it? Sine of pi on 3 is root 3 on 2. So related acute angle is pi on 3. So pi on 3 would be a solution on the boundary. Second quadrant is pi minus theta, so pi minus pi on 3, and then we've got pi plus pi on 3. And then we've got 2 pi minus pi on 3 for the fourth quadrant. So simplifying, we get pi on 3, 2 pi on 3, 4 pi on 3, 6 minus 1, 5 pi on 3. Alright. So this is what we got. Now to make it all make sense, this is the boundary. We want to know where is it greater than or equal to 1.5. The absolute value greater than or equal to 1.5. I think it's easiest just to do a quick sketch. So let's do a sketch. So I'm going to put theta here on the x-axis and x here on the y-axis, and I'm sketching x is equal to root 3 sine theta. Okay, so period is obviously 2 pi, because 2 pi divide 1. Divide into 4 sections, so we've got pi on 2, pi pi, 3 pi on 2 pi. Okay, so we got pi on 2 pi, 3 pi on 2 pi. Okay, so root 3 is here, and the sine graph starts at 0 and goes up. We'll go down to negative root 3. So that's 1 period, which is equal to 2 pi radians. And we want to know what fraction of the time is the absolute value greater than or equal to 1.5. Remembering that that means that x has to be greater than or equal to 1.5 or less than or equal to negative 1.5. Ooh. Let's go back down. Okay, so we've got our solutions here for when it equals to 1.5. So let's kind of put them in here. Put a pi on 3. Pi on, wait, hold on, pi on 3. Let's think about where pi on 3 would go. So, yeah, around there. So pi on 3 here. 2 pi on 3 would be around here. What's the next solution? 4 pi on 3. 4 pi on 3 will be around here. And 6 pi. Is that, no, sorry, it's 5 pi on 3. 5 pi on 3. Okay. So at those heights, it should be about 1.5. That's where it should be 1.5. And for these guys here, it should be about negative 1.5. So there's our sine graph. We get distortion whenever we are greater than or equal to 1.5, which will be this section here. And we also get distortion when we are less than or equal to negative 1.5, which will be this section here. So, fraction now let's look at the wording. Is it fraction produce distortion? Well, let's think about in one period. One period's 2 pi, so we'll put the 2 pi down the bottom. The fraction here, this distance here is from 2 pi on 3 to pi on 3 to 2 pi on 3. If you minus, that's pi on 3. And this section here is from 4 pi on 3 to 5 pi on 3. If you minus, that's another pi on 3. So that's what you get. Or simplifying, that's 2 pi on 3, all divided by 2 pi. And if you do that, you get 1/3. So therefore, the answer to the question is the fraction where we're producing distortion when the signal is played continuously is 1/3 of the time. So 1/3 of the time. I like that question. It was interesting. You didn't even need the auxiliary angle because the phase shift didn't make a difference. It was just, the key idea was just focus on one section. So I focused on one period and then focus on for what fraction in that one period is there distortion, i.e. we were greater than or equal to 1.5 or less than or equal to negative 1.5. Okay, good luck doing 8.1 and the Smarter Math. See you in the next video.